All right, so let's take a look at the problem that we were looking at in class. That basically, while you're never going to have to do this on the AP, partly it's just this idea of learning how to work with these and being able to recognize and understanding the process of what's going on. But I would never ask you to do something like this actually on a test. I might give it something simple where I only have you do with x squared or x squared minus a constant, so it doesn't quite have so much heavy intensive algebra manipulation in it, but it is a good exercise for you guys to play around with to make sure you understand the concept of what we're doing here. All right, the first thing is that we're trying to calculate this area, and I've graphed the function right here, and I also went ahead and shaded the area under the curve that we're going to be looking for here from -1 to 1. So the first skill when you are finding this area using the limit definition, this is kind of like if you had to find a derivative using the limit definition, it's the long way. Okay, we're going to obviously come up with some shortcuts soon. But if I want to find this area, your job is to be able to write it as a limit with a summation in it. So we're going to do the limit as in the number of rectangles goes to infinity of the sum of the area of each individual rectangle. So we're going to add up the sum, the area for n rectangles. Our delta x, so I'll come over here, our delta x is 1 minus -1 divided by n, or 2 over n. So I'm going to be using that for my delta x, 2 over n. Then what we're going to do is we're going to need to have a choice of an endpoint when we draw a rectangle. Like if I'm going to draw a representative first rectangle, I'm going to decide, and I pretty much always decide if I'm the one that has to do this, to do the right endpoint when you're looking at it, because that is always the easier one to take a look at. So your right endpoint is going to be your a, -1, plus your delta x, 2 over ni. Okay, so we're basically going to be doing our function with plugging this in for CI. Maybe we'll show it in 2 steps. I'm basically going to do CI squared minus CI cubed. And so what we've done here, just again recapping, this is your delta x, this is your f of CI, the height of the rectangle, times the width of the rectangle, which gives me the area of one rectangle, and I do this for all n rectangles, so I sum up the area for all n rectangles. This portion right here is your Riemann sum. And then once we take the limit as n goes to infinity of this Riemann sum, that gives us the exact area. This part is an approximation of the area, but as we let n go to infinity, increase the number of rectangles, it will converge on the exact area for us. All right, so then from here, that's the one thing we have to recognize. So we're going to go ahead and start working through this problem. I'm actually going to apply the function and plug my CI in. So it's going to end up being 2 over n times my -1 plus 2i over n squared minus -1 plus 2i over n cubed. Now remember from here, what your objective is going to be in a problem like this is that we need to basically remove the sigma. And the only way to remove the sigma is we need to get this so that we have the sum of a sum or difference so that we can distribute through. Now, we're going to choose to be smart about how we do our algebra though, because we really don't want to have to be cubing out this whole thing. We first want to recognize we have a common factor. So I'm going to pull the common factor out. I also recognize that the variable of this summation is I. So this 2 over n that's right here is a constant. So I'm just going to pull that out and then start with the sum again. But I'm going to factor out a GCF. So I'm going to factor out -1 plus 2i over n squared. and then I'm going to look at what I have left after I take that out. From here I would have a 1 in this first term, minus, now over here I'm going to have one of them left, 2i over n. Okay. I'm going to simplify inside of the parentheses here. And like I said, a lot of this is tedious because you have to continually write down all the parts. Now, kind of planning ahead while I'm here, I'm going to go ahead and multiply this out because I have to get it to the sum or difference. So I'm going to go ahead and FOIL this out while I'm here. So I would have 1 plus, squaring this would give me 4i squared over n squared. And then the middle term would be minus 4i over n. Simplifying over here, I'm going to get 1 plus 1, which is a 2. And then minus 2i over n. So that gets me to there. And again, I'm still not quite to a sum as I still have a product in here. Now I am just going to go ahead and distribute through here. I'm going to move over a little bit, give myself a little extra room now. Limit as n goes to infinity, 2 over n, sum I equals 1 to n. Multiply the 2 through first, so we'd have 2 plus 8i squared over n squared minus 8i over n. And then I'm going to take the minus through, so minus 2i over n. Then this one would give me minus 8i cubed over n cubed. And then distributing the last one would give me plus 8i squared over n squared. And I looked at this earlier, and let's put parentheses here as we go. Either way that we do this, at this point you really just want to go ahead and distribute this through and maybe collect some like terms as you're doing it. I'm going to actually go ahead and collect some like terms because I think that will make this just a little bit easier. And I know I took this 2 over n out. I'm actually going to put it back in so that way I have one nice clean summation so that I can then distribute and take the constants out and see how that works. So I'm just going to rewrite it again one more time, and this is more because this is heavy algebra. I equals 1 to n. If I multiply that through, I would have 4 over n plus 16i squared over n cubed minus 16i over n squared minus 4i over n squared minus 16i cubed over n to the 4th plus 16i squared over n cubed. And then at this point, I am going to see if there are any like terms that I can combine together. So limit as n goes to infinity, sum I equals 1 to n. I only have this one constant, 4 over n. Now I have an I squared over n cubed, I squared over n cubed. So I have 16n, 16 gives me 32 of those. Then I have a minus 16i over n squared minus 4i over n squared. So I have minus 20 of those. And then I have this minus 16i cubed over n to the 4th. Now I'm going to go ahead, after I've done all of this has just been algebra to get myself to a sum or difference that I can distribute that through. So now we're going to distribute the summation through. Limit as n goes to infinity. That's just a constant. I'm going to pull the constants out. 32 over n cubed, sum I equals 1 to n of I squared, minus 20 over n squared, sum I equals 1 to n of I, minus 16 over n to the 4th, sum I equals 1 to n of I cubed. All right, and let's do parentheses. We know that's all still in the limit. Now I'm going to apply those formulas that we had for the closed formula to remove the sigmas. Remember, this is a constant, so the sum of a constant is going to be the constant times n. Then I have my 32 over n cubed, which is the constant, times the sum of I squared, and the sum of I squared is n plus 1, 2n plus 1 all over 6. Then we have our minus 20 over n squared, the sum of I, which is n plus 1 over 2, minus 16 over n to the fourth. Now I have the sum of I cubed, which is going to be n squared. Let's see if I can fit this in here. N plus 1 squared all over 4. So at this point, I have gotten rid of all of the sigmas, but what my problem is going to be is that now I need to get this into a single fraction. Now, I will say the nice thing about this is we only care about the dominant terms. So the first thing I'm going to do is think about what would be my common denominator. So I look at the denominators, and as you scan across your denominators, you see that you have n to the fourth is going to be the biggest power that you need. And then I have a 4, a 2, and a 6, so I'm going to need a 12. So I look at my common denominator, and then I go in and I'm going to add the pieces that I need. So this is only an n, so it's going to need an n cubed on the bottom and an n cubed on the top, so that would make that a 4. Then we need the constant, so we're going to have to go 12 and 12. So I add that in. I come to this one. This has a 6n cubed, so it's missing an n, and it's missing a 2. So I need to multiply by 2n over 2n. This one has a 2n squared, so it's going to need an n squared and a 6. So I put that in for multiplying. And then over here, the only thing I'm missing is a 3, so I'll just do a 3 there. So I kind of add in what I need for my common denominator. And then here's where the magic starts to happen. I don't care what all the terms are. I only care about the biggest term. So like if I'm looking at this, because I'm going to add all the tops together. So I come across through the tops, and I basically just need to figure out what the dominant terms are going to be in each one. So when I write it down here, I'm looking for the dominant term. So we have a 4 times 12 times n to the fourth. So that's pretty much going to be 48 n to the fourth from the first term. Now from the second term, all I really care about, remember, is the dominant one. So I'm going to have the 2n, the 32, and then I'm going to need to get the highest from each of those. And if I were to multiply 2 times 32, 64, times 2, 128, and then I have 1, 2, 3, 4 n's. So that's plus 128 n to the fourth. The rest of the stuff doesn't matter because it's lower degree, so in taking the limit it's going to drop out, so I can ignore them. Alright, over here I'm going to do the same thing. I have 6n squared and a 20, and if it helps you can highlight what you want. 6 and n squared, this 20, an n and an n. So I have n to the fourth and then 6 times 20, and 6 times 20 is 120. So, and it's negative, don't forget the little minus right there. So we would have our minus 120 n to the fourth from this term, and something else, but we don't care about that. And then from this last one, we are going to take each of these terms. So we're going to have the 3, a 16, an n squared, and n squared there. So we pretty much have 3 times 16, and again it's a subtraction. So we end up with minus 48 n to the fourth. So I cherry pick only the highest degree from each of the fractions to add together, knowing that I'm going to take the limit. So that way I don't have to do all the manipulation of all the rest of it. I mean, it's bad enough as it is. So the limit as n goes to infinity, then I combine all of these together and some nice cancellation happens. These are gone. 128 minus 8. We basically get 8n to the fourth over 12n to the fourth. Remove the infinity over infinity indeterminate form, and then we simplify. Our limit is going to be 8/12 or 2/3. Okay, and so the exact area under this curve is going to be 2/3. And then let's just verify that with the calculator. So I'm going to quit out of that and take my definite integral. I'm just going to cheat. I'm going to go get this since I already had y1 in there. And we're doing from -1 to 1. So let's go down to our bottom here. -1 to 1. And then I can hit enter and get my 2/3 that I just found. So that's walking you through, a fairly difficult and heavy algebra intensive problem. But again, the idea here is that you need to be able to, on the actual AP, in a multiple choice question, if you see something like this, to recognize that it actually is the area, and to understand that we really at this point don't want to be doing this for a long time to find an exact area. That what I want to do is have this idea, which is what's coming in the next section, is that a way to find this area, that this area from -1 to 1 on this function f of x dx is nothing more than a definite integral. And what we're going to work toward is coming up with a shortcut in order to calculate this definite integral. And we'll be talking about that in the coming lessons.